Hello everyone, my name is Jianan Duan and I am a postdoc researcher at Télécom Paris, which is part of Institut Polytechnique de Paris. The work that I'm going to present with the title of Dynamic Properties of Two-State Lasing Quantum Dot Laser for External Optical Feedback Resistant Applications is collaborated with Shanghai Tech University. Firstly, I would like to talk about the external optical feedback. The above figure gives a simple feedback scheme, where the laser is placed in an external cavity made by a mirror, and the light is then back reflected to the active region. The spectral mapping on the right of a Fabry-Pale laser, along with the feedback strengths, showing the root to coherence collapse regime, occurs due to the undamping of the relaxation oscillations. The critical feedback level can be estimated from the relationship below, and it indicates the maximum feedback ratio for stable operation into a communication system. The critical feedback level depends on the damping factor and the linewidth broadening factor. Our previous works have shown that the critical feedback level in quantum dot lasers depends on the ratio between the ground state threshold and the ecstatic state threshold. When this ratio is small, the laser is more sensitive to external optical feedback. On the other hand, at a fixed ratio, the laser is more sensitive to optical feedback at ecstatic state threshold. In order to explain this phenomenon, we develop a complete two-state lasing quantum dot laser model. This is the outline of my presentation. I will begin by introducing the merits of quantum dot laser. Then I will present our numerical model of two-state lasing quantum dot lasers. The next part will present the optical noise and the dynamic properties. Finally, based on these studies, I have conclusions and perspectives of my future works. As shown in the figure on the left, decreasing the degrees of freedom of carriers leads to the formation of low-dimensional nanostructures such as quantum dots. Ideally, quantum dot systems exhibit an atom-like downstate of state, hence providing an ultimate carrier confinement. Thus, compared with the quantum wheel, the quantum dots are advantages for the laser devices such as low operating current and large thermal stability, as shown in the figure on the right. In addition, thanks to the low sensitivity of nanostructures to epitaxial defects, quantum dot lasers have been successfully grown on silicon. Due to the slow intraband relaxation and unclamped gain, the quantum dot laser can emit on the sole ground state and also on simultaneous two states. The light current curve and optical spectrum show that with the increase of the bias current, the laser firstly emits on the ground state, and then simultaneous on two states, and finally on the sole ecstatic state. Here I compared some dynamic properties among the sole ground state emission, sole ecstatic state emission, and two-state lasing. The GS is known to have larger damping factor, hence provides high optical feedback resistance. But it also has limited modulation bandwidth. Compared with GS emission, the ES emission has smaller damping and a higher material gain induced near zero linewidth broadening factor. Thus, it has high optical feedback sensitivity and better modulation performance. As for two-state lasing, It has shown to have lower intensity noise than the single-state lasing. The figure also shows that the two-state lasing has enhanced modulation bandwidth. The figure shows the principle of the dynamics of the carriers in quantum dot lasers model. The dynamics of the carriers between the carrier reservoir and the states of the quantum dot, that is to say the ecstatic state and the ground state, are controlled by the different characteristic times, such as the relaxation time, the capture time, and the escape time. The differential rate equations describing carrier, photon, and phase dynamics are expressed on the left. In the equation, the term F represents carrier noise and spontaneous emission noise. The modeling of the laser is done in two steps. Firstly, we transpose the system in the frequency domain. Then we consider the correlation strength between two Langevin noise. Finally, we use a small signal approach applied to the equations, and hence we can obtain the expression of the relative intensity noise, the frequency noise, the intrinsic linewidth, the shallow tone linewidth, and the linewidth broadening factor. Now I will present our simulation results. Firstly, I give the light current curve of the laser. The GS threshold current is found to be 49 mA and the ES threshold current is 284 mA. Thus, we divide the LI into two parts. Before ES, we only have GS emission. After ES, we have both GS and ES emission. The figure on the right shows the relative intensity noise at 1 MHz as a function of bias current. In the sole GS regime, the GS ring firstly decreases and then re-increases to minus 140 dB per X at ES lasing threshold, which is due to the spontaneous emission of ES. In the two-state lasing regime, the GS ring keeps constant, while the ES ring decreases with the bias current. As for the intrinsic linewidth, the tendency is similar as the ring. The GS linewidth firstly decreases and then re-increases to 2 MHz. Here we conclude that both the ring and linewidth have a local maximum value at ES threshold. Now the figure shows the results of linewidth broadening factor, also named as alpha factor. The GS alpha factor increases from 0.7 to 1.2, just below the ES threshold. However, the GS alpha factor dramatically increases to 2.9 at ES threshold due to the strong carrier perturbation of ES emission. At two-state regime, both GS and ES alpha factor keep constant, since the ES simulated emission stabilizes the carrier vibration. The figure shows that the damping and relaxation oscillation frequency also have a local minimum value at ES threshold. This is because the dominant contribution of the ES spontaneous emission. Now we have known that both the alpha factor and the damping factor have the local extreme values at ES threshold current. The figure shows a comparison of critical level between the simulation and the measurement. The simulation is in agreement with the measurement, shows that quantum dot lasers have strong stability against optical feedback before and after ES lasing threshold. The lowest critical level at ES threshold results from the maximum linewidth broadening factor and minimum damping factor. In conclusion, this work gives a complete numerical study of two-state lasing quantum dot lasers, including the carrier noise and spontaneous emission noise. Optical noise performance stressed that practical applications of quantum dot lasers should avoid current operation at ES threshold. The local extrema of both damping and linewidth broadening factor at ES lasing threshold make the quantum dot laser more sensitive to optical feedback, which is in agreement with the measurement. Our future work will focus on numerical model of silicon-based quantum dot lasers, and we will also investigate of optical feedback and optical injection dynamics. Thanks for your attention.